weaker acid, which releases less hydrogen ions. Since we're talking about breaking apart and ionizing, these types of chemicals are not covalently bonded, these are ionically bonded. So you might recall in previous discussion, perhaps from Bio 210, acids are things like hydrochloric acid, our stomach acid of course. Other examples of acids include hydrosulfuric acid or just sulfuric acid, phosphoric acid, and you'll notice that what they all have in common is the presence of hydrogen ions at the start of the compound. We actually have not had enough chemistry in this course or in our background to discuss which one of these will be strong acids just by looking at them. That would take say a Chem 110 type course to make that prediction. But we can at least look and say each of these starts with a hydrogen, it likely is going to be an acid because of that reason. We can't really look at these and say, hey, these are going to be strong or weak, but at least we can qualify that they're acids. When we talk about strong acids, we talk about more release of hydrogen. Weak acids still release hydrogen ions, but they're not quite so readily available. That chemical compound is not quite so willing to give up or donate its hydrogen. So in comparison, if you take something on the pH scale, for instance, stomach acid approximately has a pH of 1 or 2. If you compare that to other acids on the pH scale, we can quantify how strong an acid is or how weak an acid is compared to other pH values.
Is there a zero?
There's a zero. In fact, there's negative 2.
Really?
Yeah.
Wow.
So this is just, I guess you'd say, the more common numbers that we use. Let's say that we've got stomach acid with a pH of 1. If we want to actually quantify or make into numerical comparison how strong 1 is to, say, 2, we can say that pH of 1 is 10 times stronger than a pH of 2. That's because the pH scale is based on logarithms. This time the logarithm is based on the number 10. So every whole number that you move on the pH scale is going to be a 10-fold change in acidity or alkalinity. Alright, let's say that a person has a pancreatic disorder. This is going back a little bit into the digestive function. What does pancreatic juice do to the chyme entering your duodenum? Neutralizes it, right? Brings the pH up closer to blood pH, which is 7.4 on average. Let's say that the person is not releasing enough pancreatic juice. Instead of absorbing neutralized chyme into the bloodstream, this person is absorbing quite acidic chyme into the bloodstream. That's like adding a very strong acid into the bloodstream. That strong acid can bring your blood pH where? Down. Bring it down. Hydrochloric acid, if it's say pH of 1, if you add hydrochloric acid pH 1 into your bloodstream, that's going to bring your 7.4 blood pH drastically down. Under normal conditions, if we were to do this in a beaker and we had, say, 7.4 and we added in hydrochloric acid, you would see that the pH would drop drastically. But we actually have something in our bloodstream that prevents the dramatic drop and rise of blood pH. Those things are called buffers. So they actually help, modify the type of acids and bases that may enter our bloodstream, and they have less dramatic effect on our overall blood pH. So, thinking about the pH scale here, acids can drop the pH of our bloodstream. If you add bases in, they can raise the pH of our bloodstream. So anything that's found above 7 on the pH scale is known as a base or an alkaline solution. So at the area here close to 7, do we consider those weak or strong?
Weak.
Those are weak bases. Likewise, if you add a strong base to the bloodstream, that pH can rise. But we're lucky that we have these buffers in our bloodstream that help to essentially not to use the same word for the definition, but buffer or reduce the effects of the acids and bases added to our bloodstream. Do you recall from Bio 210 how you do this strength change, 10, 100, 1,000? Do you need a quick review of that?
Add a zero every time you change the number?
Add a zero every time. Let me give you a quick example. If you're comparing a pH of 5 to a pH of 2, that's 10 to the third. That also tells me I've got 3 zeros. Okay, so that's probably the easiest shortcut way to figure it out. Do you need another one like this? 12 and 8. Okay.
That's on the bottom page, it's showing 1,000, but shouldn't it be 10,000?
Yeah, it should be 10,000. Do I have an error down there? Yeah. Okay. Oh yeah, that's, look under page 134, down there about below the halfway point of the page. Clorox pH 12, it says is 1,000 times stronger than seawater. You're right, that should be 10,000 times stronger. Thanks for pointing that out. Okay, so that's basically an overview here of page 134. Just want to go back and revisit the pH scale for you. I know it's been a semester since you've probably heard information on pH. Let's take a look over on page 135 because this gets us more to how the body accommodates for changes in pH. So if you have something like stomach acid that's being absorbed into your bloodstream, normally something like a pH of 1 would have a dramatic effect on your pH, which is 7.4 in the blood. But thanks to these chemicals in your bloodstream known as buffers, the pH change is less dramatic than it could be. That helps us to maintain homeostasis more effectively. So we're looking at buffer systems in the top of 135 as a way to help maintain blood pH.
And what is in the pH in the stomach? 1 to 2?
1 to 2, yeah. pH in the stomach is around 1 or 2. There's actually several different types of buffer systems. If you've read your textbook, you'll notice that they talk about a phosphate system, a protein system, and most important for us is the bicarbonate system. So what I focused on here on your course pack, page 135, is the bicarbonate system. That is the most important of the buffering systems in our bloodstream. So let's talk about these three chemicals here. You'll see these three types of chemicals commonly in our discussion of the bicarbonate buffer system. The first one here, HCO3 with a negative ion charge there, that one's known as bicarbonate ion. We've talked about this one before back when we studied our respiratory system. This is the end result typically when you have carbon dioxide dissolved in the bloodstream. This is a new one for us. It's called sodium bicarbonate. You'll notice that sodium is hooked to the front of that compound. And here's another one. You've got hydrogen hooked to the front of the compound. This one is H2CO3. Notice there's no negative charge on this one. It's not an anion. It's just a compound creating an extra hydrogen ion.
So number 2 should have a
NaHCO3.
should be H2CO3 instead of HCO3 because it says it forms carbonic acid.